Okay, we're going to get to a GCM, but I want to formulate mathematically a key aspect of the kind of data that we're going to encounter in a GCM. And I'm going to frame that in terms of data which is calculated through time averages. Okay? So the setting is that I'm going to work with a system of ordinary differential equations parameterized by a theta that we want to learn. I'm going to assume that the data we have is found as a function, which is a time average over a time interval of length t of phi, or var phi. There will be another phi in the talk later. So var phi of u of t. So I just observe some aspects of the system time averaged. And if I assume, and that is an assumption for this talk, that the underlying differential equation is ergodic, so there's enough chaos in the system to give ergodic behavior, this time average, as t goes to infinity, will converge to something that's independent of the initial data. However, in practice, we have time averages over a finite time interval. And so the observation function g is parameterized by t, the time interval over which we average, and by the initial condition u0, which we don't know. So a key point to understand in climate is that we are given data, we don't have the initial condition. In fact, finding the initial condition is not an object of interest in the way it is in weather forecasting. So the initial condition is a nuisance parameter, but it's present in here in a way that you'll see in a moment. So the data is time average. It depends on the initial condition, but that dependence disappears as the time horizon becomes longer. So I can formalize that by writing a central limit theorem. And there are central limit theorems for a few deterministic dynamical systems, Lorenz 63, for example. Mostly, these are not proven for deterministic problems. And you don't require the details of this 1 over root t dependence for what I'm going to say. But you do require ergodicity, which says that as t goes to infinity, the dependence on the initial condition will wash out. But very specifically, we can express that through a central limit theorem, which says that this time average, which depends on the initial condition, is equal to the infinite time average, which doesn't depend on an initial condition, plus something small and random. And the sense in which it's random requires a probability measure, which you can think of as the probability measure on a climatological attractor, and the fact that you think of u0 as being randomly picked from climatology. Okay, so the data we have, gt, depends in an unpleasant random way on something we don't know. But there's a limit if we had an infinite amount of data where the nuisance parameter disappears. So therefore, I can think of the data y as being given by this infinite time average plus something which gets small when the time interval is long, but is random. And you'll see this in a second. The effect of this randomness you'll see. So the key point to appreciate here is that I want to invert g for theta given y, but I don't actually have g. I just have g sub t, which is a noisy approximation of g. And so this is a surrogate for a simple mathematical exposition of what a lot of time average data looks like in many applications, including climate. So let me take you through some of this in the context of a really well understood example before I go to a GCM. So this is one for which all the theory I just described applies. So these are everyone, I think, will know this system of equations. I fixed this parameter at 10, which is the classical parameter for chaos. And I'm going to try and learn the parameters r and b from data. And data will be generated at the classical chaotic parameter values, which I'll come to in a second. So this is just the two-dimensional unknown, theta, which is r and b. My function var phi, the quantities which I'm going to know time averages of, is going to be x, y, z, x squared, y squared, z squared, and x, y, x, z, y, z. So all of the first and second order, first and second, that's the coffee again, all of the first and second order statistics of these equations. Okay, so we have time averages of the first and second order statistics of these equations up to time t. And again, to re-emphasize, we want to invert g, but only available to us is gt, which depends on the initial condition, whereas g does not. And the noise, eta, is only available to us approximately via g sub t. Okay, so I'm going to use the Ensemble Kalman inversion in the continuous time formulation I described to you at the beginning of the talk. It's this interacting particle system. You probably can't take it in. What matters here? So this is a system of particles. We typically, in the experiments I'm going to show you, run it with several hundred particles over between 5 and 50 time steps. G, although for Lorenz 96 it's not terribly expensive, when I do a GCM afterwards, evaluation of G is expensive. Every time I evaluate G, I'm running a GCM with the parameter value that you see here. Okay? So this is a system of ordinary differential equations, which looks simple, but the right-hand side involves G, which is evaluation of a GCM. Okay? So this is a big system of ordinary differential equations. It's expensive. So the two unknown parameters are the classical values, 28 and 23, and the data is just found by the time averages over. I should have answered the question a bit more clearly. There is a time horizon over which we integrate, which for this problem would involve going around the attractor several times, but not necessarily completely getting rid of the initial condition in the averages. So just to re-emphasize, we don't actually have G. It's only available to us approximately via GT. So if you could show, I'm sorry, now thank you for this. I'm going to show you an algorithm just before you run it. So these are the two parameters, and this is the initial ensemble. And in the background are the level sets of y minus g of theta squared. So that's you've solved the problem well if you're over here and not so well over here. These particles interact, and they're going to interact according to the flow I just showed you. The right-hand side of that equation involves computing true time averages of the Lorenz 63 system at every time step. So thank you. If you could just show me how this. I'm not competent with this computer. What you're going to see is an evolution of these particles. And no, it's the other one, sorry. Thank you. So the particles evolve. Thank you very much. Particles evolve under the algorithmic time in the fashion that you see here. So they're interacting with one another. They're learning where they fit the data well, and they're collapsing. So those are two features that are common to Ensemble Kalman inversion. You match the data well, and the particles collapse. And in fact, you can ameliorate collapse by adding noise into the system, and that's what a lot of people are doing in this area, is to try and add the optimal amount of noise so that instead of collapsing, actually there is in this system noise, but anyway, only a small amount. A game that people are playing is to add noise to this system so that the spread in these particles at the end captures the true posterior. Okay, my perspective is that that's a very difficult game to play, especially as we only have a small number, in general, well, here not the case, but in general we only have a small number of particles relative to the dimension of things we are learning. So I'm going to propose a different method of using this output to do uncertainty quantification. Thanks very much. But I hope that demo gave you some indication of what the Ensemble Kalman flow does. The take-home message was, just to repeat, that it's a flow which, thank you, encourages the particles to move towards the data and encourages the particles to form consensus. And there's a whole field of consensus-based particle optimization that has nothing to do with the Ensemble Kalman filter. And I think for this community and that community, it would be very interesting to link those two perspectives together. Ensemble Kalman Inversion has evolved very much in the context of specific geophysical applications, weather and subsurface inversion. But there's a whole community out there of optimization involving interacting particles, derivative-free. And I think linking them would be a good idea. Because if you're just interested in optimization and you don't see the method as one which correctly computes uncertainty, then there's a whole load of freedom in what you might do with the algorithm to improve it. So here's one thing you could do, and I want to tell you how that works. So what I'm plotting, as I mentioned, we're trying to solve the inverse problem of matching theta under the image of a complicated map G to data Y. So we want to, you can frame that as a least squares problem of making this phi, that should be phi of theta, making phi of theta small. Okay? What makes this problem particularly interesting is we don't know G. We only know G sub t. And what I'm plotting here in blue is what we actually compute, not G, but it's this phi against, I fix one parameter and plot against another. I'm plotting phi, not with G here, but with G sub t, which is actually available to us through finite time averages. And what you see is a very noisy objective function. So one of the beauties, one of the beauties of the Ensemble Kalman method is that it's very fault tolerant to this kind of noise. The algorithm I just showed you, the smooth progression of those particles, was using exactly this kind of noisy evaluation of the inherent loss function in here. And it really performs well in that context. But as I'll show you in a minute, Monte Carlo Markov chain is not fault tolerant to this, and we need to get rid of it. So what I'm going to propose is that we learn the smooth function underneath here by using Gaussian process regression. And in this particular example, I'm going to apply that to GP emulation to log of phi. There are many things you can do in this area, and we're just beginning to explore them, but this is one. And then the shaded orange bands that you see are 95% confidence intervals for the function phi, which is the large time limit, if you could integrate forever, as estimated by Gaussian process regression. So there's a smooth envelope to this nasty blue curve. At the moment, in this example, the Gaussian process regression doesn't use Ensemble Kalman Inversion, but I'll show you when we do the GCM how to do that. But here we just do some form of GP regression to get a better approximation of this noisy objective function. And then I'm not going to write down Bayes' theorem, but I can write down a Bayesian version of the problem I described to you, which is to find the probability distribution of the parameters theta given the data. The data is, as I said, viewed as a noisy approximation of the infinite time average. And the GP enables us to estimate the size of the noise and gives us a smooth approximation of the forward model. If the forward model you would get by integrating on an infinite time horizon. The key point is that if you don't use the Gaussian process regression and try and use MCMC on the noisy data, you can't converge it. So we have here done 50,000 samples of Monte Carlo Markov chain, a tuned random walk metropolis. We're only getting a 1% acceptance rate for the actual phi. And the reason for that is because the actual phi is incredibly noisy, and you easily get stuck in local minima on this noisy blue curve. And you don't care about those. That's the wrong those are the wrong places to be. You want to be down here at the minimum of this smooth function. When you do the GP regression, however, you get a smoother energy surface, and we're getting 30% acceptance rate. And this Monte Carlo Markov chain using the Gaussian process is converged, and that one isn't. So the take-home message from this example is that we can, by using Gaussian process regression, extract a smooth function G from which it is appropriate to apply Bayes' theorem. The challenge I'm going to take on in the next talk is to try and use output of the Ensemble Kalman inversion to train that Gaussian process, therefore to build something which is no more expensive than, in terms of the number of forward model evaluations, no more expensive than doing Ensemble Kalman inversion. But we will get a Gaussian process approximation of the full Bayesian posterior distribution. So I'm going to exemplify that idea in the context of, I'm not an expert by any means in climate modeling, but we're going to use something called the Betz-Miller scheme, which I'm going to describe to you now. But this is a simple subgrid scale model. So we're solving this on it's an aquaplanet. I've here written the equations for moisture conservation and energy conservation, and these are coupled to mass and momentum conservation. And there's on the order of 10 to the 5 unknowns at the level of discretization that we are using. The basic idea of the subgrid scale model is this, that the model predicts precipitation rates either using moisture conservation equation Q or temperature T, and those should be equal, but they're not. And so you can drive through subgrid scale modeling those two estimates of precipitation rates to be equal. And that's the purposes of these terms here. So these terms are parameterized by two parameters in this example, theta, which is a reference relative humidity, thank you, and theta t, which is a default relaxation timescale. Okay, so we're going to try and estimate these two parameters, theta, from data. And data will be time averages computed from this equation. And I'll be precise about them now. The algorithm you're about to, the algorithm we'll run will be, this is actually the standard discrete time ensemble Kalman inversion, not the continuous one. And the data we have is computed by looking at the relative humidity and the daily precipitation rate, averaged longitudinally, and of course averaged in time. Everything in this section of the talk is averaged in time. But allowed to vary with respect to latitude. And F here is a longitudinal probability, looking at the probability distribution longitudinally of extreme precipitation. So that data is a data of a vector of size roughly 100. And we estimate it, and we get that by looking at this quantity, which is averaged longitudinally and in time, by evaluating over all of the latitudes that are free on the grid, at a fixed altitude of 5 kilometers. The algorithm I'm going to show you, I need to disturb you again to show you one more. So this is a set of parameters which I'm now going to run under the Ensemble Kalman inversion method. Each step of Ensemble Kalman inversion involves multiple runs of the GCM that I just described. And if you could go ahead and show it. So this is a discrete time, not continuous time algorithm. And the crosshairs indicate the true value of the parameter. So what you see here is, as before, the particles in a small number of steps reach consensus and agree upon a value. And that value is very close to the true value, which is at where these red dotted lines meet. Okay, so this is not a smooth evolution the way I showed you before, because I'm not doing a continuous time algorithm. But it has the same two features, driven towards the data, fitting the data, and therefore successfully recovering the true values of the parameter, and driven towards consensus. Thank you, that's great. But again, to emphasize, there's much work in this area of Ensemble Kalman inversion, which is taking the basic algorithm I've described and adding noise to it, so that the point that you get, thank you, the point that you get at the end, the set of points that sit here, have a spread which represents the true posterior distribution. I'm not going to do that. I'm going to take the output of these, train a Gaussian process on them, and use that Gaussian process in a full Bayesian quantification of uncertainty for the parameters. So again, just to show you that there's a noisy objective function here. We can train a Gaussian process on it. That's this dark orange curve, and that comes with uncertainty quantification. We can use that to train a Gaussian process, and then do full Bayesian uncertainty quantification using Monte Carlo Markov chain. This is an impractical algorithm, but it's put there for comparison. It's impractical because here we've done a Gaussian process regression using a uniform set of samples across the whole grid of parameters. For real climate models, not just this toy aquaplanet, that would not be feasible. This, however, would be feasible because I've trained the GP only on the output of Ensemble Kalman Inversion. So the philosophy here is use Ensemble Kalman Inversion to learn parameters with the full GCM, and that involves only a few hundred evaluations of the forward model. Then train a Gaussian process based on the output of Ensemble Kalman Inversion, and using that Gaussian process, do MCMC. And this is the posterior distribution on the two parameters which results. Okay, so that was the end of the second section. Thankfully, my third section is very short, so I'm going to go through it in, the bell's going to ring in a minute. I'm going to go through it in a couple of minutes. But this is a simple idea that I just want, so in the second section, my main point was that many problems, the data comes in the form of time averages. Conceptually, we like to think of the time averages over infinite time horizon. In practice, we only have them over finite time horizon. But we can use Gaussian process regression to help us find the infinite time averages. And that helps us do both the parameter estimation, but more importantly, to do the uncertainty quantification using a fully Bayesian formulation. Okay, from the optimization perspective that I gave you at the beginning follows a really simple idea, and I just want to tell you that. What I'm going to describe is in this paper of Janczyk, McLaughlin, and others in 2014 in a very specific context, and all of the credit for this idea, which I think is beautiful, should go to these guys. This is a great paper, and I just want to show you it in a very general abstract context concerned with inversion rather than state space estimation, which was their context. It's a really simple idea, and even if you forget everything else I've told you, you can remember this because it's, I think it's very transferable. Applies in many, many contexts. Right at the beginning, I formulated the Ensemble Kalman method, Ensemble Kalman Inversion, by writing things in state space form, starting with the Kalman filter. So let's just look at the Ensemble Kalman filter for state space. This can also apply to Ensemble Kalman Inversion in the same way I showed you before. I formulated it as let's predict using the model, and then let's solve a quadratic optimization problem. And just remember, the whole point about Kalman is you can solve the quadratic optimization problem by pencil and paper and write down the answer, and that gives you Kalman gain and all the formulae you're familiar with. But let's not do that. Let's just keep it as a quadratic optimization problem. Then, and this is the idea of the paper of McLaughlin and others, I can just append that quadratic optimization with, in fact, if I constrain this minimization over a convex set, there will be a unique solution. I can't write it down in pencil and paper the way I can write down Kalman gain, but in terms of functionally, in terms of an algorithm, the algorithm is very much the same. I replace the Kalman gain formulae by solving an optimization problem, and here I'm doing it not just over convex constraints, but linear equality and inequality constraints. So you just, to make this algorithm work, you just predict in the normal way as you do in Kalman filter, and then instead of using Kalman gain formula, you solve a quadratic optimization subject to linear equality and inequality constraints. You can view that as a solved problem. There's fantastic algorithms and software out there to do it. Actually, this is an interesting conceptual point. Old people like me grew up thinking in everything in terms of pencil and paper, right? What you think of as an algorithm is something you can write down. But we're moving to an era where the younger people in this audience should be able to accept this idea. The basic primitives with which we work are not algorithms that you can write down on a piece of paper, but pieces of software code that are reliable and solve in a provably accurate way certain problems. So this problem, quadratic optimization subject to linear inequality and equality constraints, that's a solved problem. I can't write down the solution analytically, but you can solve it. So why not just think of that as a perfectly, just the same as I would have thought of a formula that I can write down. All right, let me just show you an example coming from seismology. This is a problem of estimating wave speed in a subsurface medium from accelerometer measurements on the surface. So think of an earthquake in the subsurface, causes disturbances on the surface. You measure acceleration of the surface, and you try and learn the material properties of the subsurface. Let me just show you a picture of where I'm going. This is in black here is the true material subsurface, and the red is what we learn by this method. We parameterize the subsurface, and in this particular case, you won't take this in, but this is a particular parametric form of a function that's commonly used in seismology in this context. It has 6 unknown parameters, and for physical reasons, they are constrained in certain ways. You can run the Ensemble Kalman filter the way I've described, and this is the evolution of the particles. And this shows you the percentage as the iteration proceeds. This color code, dark blue, shows that no constraints are violated. And what you see in this algorithm is that early on you violate constraints. As you learn the correct parameters, you don't violate them anymore. By the way, when you don't violate constraints, the algorithm just reverts to the standard pencil and paper algorithm that you all know. Okay, I will just thank you for your attention. I just want to summarize the 3 things I've told you. Firstly, Ensemble Kalman inversion purely from the perspective of optimization. That was the first part of the talk. And I showed you in that context that choice of parameterization was key to solving complex problems. Second part of the talk was about learning parameters in complex dynamical systems from time average data. And the key idea there was that we can learn the infinite time horizon averages by using Gaussian process regression on output of models from finite time averages. And then the third part of the talk was showing how to incorporate constraints into the optimization perspective that I gave at the beginning. Thank you for listening.
Thank you very much. Thank you very much.